All right, a few quick important multiplication facts that we're going to be using in a little bit when we talk about multiplication algorithms. But they're basically all going to be based on the following things. One is knowing your times tables. So memorization isn't something you want to do for lots of things in math, but one thing you do want to memorize because it comes up incredibly often are your times tables. So just knowing the all products of all single digit numbers, as long as you know things like 9 times 7 is 63, 7 times 8 is 56, etc. If you know all of those single digit times single digit multiplications, that's going to be extremely helpful for you going forward and for the future students that you do have. So know that. And the other important thing is going to be the idea of multiplying by a power of 10. And basically all you do with that, I think everybody knows this, but I just do want to stress it. If you do have two numbers, we're thinking of this number as being the number you're multiplying, and I use this letter E to mean exponent. So if you have these two numbers, the number you're multiplying, and the exponent, the power of 10, then A times 10 to whatever exponent you like, well, you just put that number of zeros after the number. For example, if I want to do 24 times 10 to the power of 5, well, what does this mean? This means 10 multiplied by itself 5 times, so that's 1 with 5 zeros after it. So all I'm going to do is I'm going to take that number 24 and I'm going to write 5 zeros after it. I don't want to belabor this too much. I think that's pretty intuitive, and I think everybody understands why that it is the case. So between knowing your times tables, knowing powers of 10, and understanding the distributive property, then the idea of algorithms for multiplication are going to be really easy. So let's talk about how we multiply and why it works the way we do. We're going to talk about two algorithms. I want to start with something called partial product, and then we'll talk about the standard algorithm. And that's the one that I think most people use for multiplication. But they both rely on the following things. And what they rely on are your times tables, the second is multiplication by powers of 10, and the third is distributivity, but done cleverly. Distributivity by place value. And what do I mean by that? So let me give you an example first. In fact, it's something we've already seen, but we're just going to break things up a little more intelligently. So let's do just a 2-digit by 2-digit example first. And we're relying on the fact that we know our times tables and we know how to multiply by powers of 10. They're things we're going to take for granted. Okay, so imagine that you want to do the multiplication, I don't know, 24 times 37. So again, we can use that array model to help us out here. So let's say this horizontal dimension is 24 and the vertical dimension is 37. Again, you can think of this like a 24 block by 37 block chocolate bar, if you like. Now remember, if we know how to multiply by powers of 10, and we automatically know all of our single-digit multiplications, if we can intelligently break up this chocolate bar or use the distributive property to help us out here, then we're just going to use these ideas here. And of course, the way we're going to do it is we're going to break it up by place value. So I'm going to split up the number 20 and 4 into its expanded form. So it's going to be 20 plus 4. So 24 becomes 20 plus 4. And finally, 37, I'm going to break that up by its place value, write in expanded form, 30 plus 7. So let me break this up. And again, I'm not being particularly accurate about having one half have length 30 and the other have length 7, whatever. This is just kind of an illustrative diagram. So this is 30 and 7. Now again, we know exactly how to multiply single digits. So this little block here, the 7 by 4 block, we can easily figure out the area of that. That is 28. This 4 by 30 block, well, we're also using, maybe I'll put kind of like number 4 in here as well, because really we're also using commutativity and associativity, and I'll explain in a second. So if I want to do 4 times 30, so that's this block here, I'm going to put a little box here. So this box, well, that's 4 times 30. So if I wanted to, I could break this up as 4 times 3 times 10, since I know how to multiply by powers of 10. So right now it's grouped like this. So 4 times 30 is 4 times 3 times 10. But remember, multiplication's associative. So I can make this 4 times 3 times 10, grouping the 4 and 3 together. And again, if we know all of our multiplication times tables, well, 4 times 3 is 12, multiplying by 10. We know how to multiply by 10 to the 1. We take the number, we put 1, 0 after it. So in this box is 120, of course. And similarly, we do the same thing with the others. 20 times 7, well, 2 times 7 is 14. And we have 1, 0, so we put it after it. And I'm not going to write out kind of the using commutativity and associativity for this block, but it's that same idea. It's 20 times 30. 2 times 3 is 6, and we put 2 zeros after it. So if we add up all of these guys, 600 plus 120 plus 140 plus 28, we will get the area of this big rectangle, which will give us this product. And that's the whole idea basically behind partial products. So let's write this out using partial products. We're still going to write it out vertically like we usually do. So this is 24 times 37, and we're just going to do a piece at a time. So 4 times 7 is 28. So this 28 here is that guy there. And then we do, well, we need 7 times 20. 7 times 20 is 140. So we write that in, 140. We're going to add these guys up eventually. And that is, of course, that guy. Then we have 30 times 4. 30 times 4 is 120. And that is that guy. And finally, we have 30 times 20, which is 600. That is that guy. Actually, let me put an arrow here since they're all arrows. And then we just add up all of these partial products. You can see why it's called partial products, because these guys here, these sub-rectangles inside of a rectangle, are the products, and when you add them together, the subproducts, and when you add them together, you get the actual product. So 8, 2 plus 4 plus 2 is 8, and 1 plus 1 plus 6 is 8. So 24 times 37 is 888. So that's all partial products are. And we'll talk a little bit more about them later, but I do want to move on, and I want to talk about the standard algorithm. So the standard algorithm is basically the same thing. So 24 times 37. This is the one that we know and love. So let's multiply this just the way we usually do. 4 times 7 is 28. Carry your 2. 2 times 7 is 14. Plus 2 is 16. 4 times 3 is 12. So now that we're multiplying, or I should say 3 times 4 is 12. 3 times 4. But since we're over one place, we're going to move over one place over here. So we need to put a 0, or some people leave it blank. But since we're starting at the tens place here, we're going to put a 0 here saying that this is the tens place we're starting. So we have 4 times 3 is 12. Put down your 2, carry your 1. Oh, wrong color. Let's do it in black. And two times 3 is 6, plus 1 is 7, and you add, you get 8, 8, 8, just like before. Of course, it's the same thing. Let's see if we can understand what this is doing via the array. So let's write it out. What do these numbers 168 and 720 stand for? So it's the same thing. It's going to be 24 by 37. All right. So somehow we have to think what this 168 and this 720 represent. Well, let's think about what we did to get each number. Well, this number is 7 times 24, and this number is 30 times 24. That's how we did it, right? We went 7 times 24, and we got that number. And then, well, we did 3 times 24, putting a 0 here, moving over one place value, but that means we're really doing 30 times 24. So let's write that down. This is 7 times 24. This is 30 times 24. So what we really did is we took one of the dimensions and we broke it up into its place value. So say this guy here, we did 30 times 7. But we didn't break up the other dimension. We just kind of kept all of that together using our carries. So we didn't kind of do all partial products, breaking this 24 up into a 20 and a 4. So really, we're just breaking it up one way. So this is 24 times 7, which is 168. And this is 24 times 30, which is 720. So when we do the standard algorithm, all we're doing is we're breaking it up in one dimension, not both dimensions. Using partial products, we break it up in both dimensions. So that's all that's going on with the standard algorithm. So this guy, let me write that in. This is, of course, our standard algorithm. And of course, once we figure out those sub-products, we need this entire area, or the product of 24 and 37. So we just add these guys together. The next thing I want to talk about is, well, let's really understand what these carries are when we multiply. Let's do just a problem that's a little harder. Let's do a 3 by 3. So let's multiply the following using the standard algorithm. I want to talk about partial products before I do that. So let's just pick some numbers. Let's do 375 times 4, 97. 7. That will do. Now, here's a question I have for you. First, if I was to multiply these using partial products, well, how many different partial products would I have to add together to get my final answer? Have a think about that. Pause the video. Have a think about that. All right, now that you're back, if you think about it, we're going to have an array model for multiplication that's going to be breaking up one dimension into 3 pieces, hundreds, tens, and ones, and the other dimension also 3 pieces, hundreds, tens, and ones. So we can think of this as a 3 times 3, or a 9-block sub-array, if you will. So we'd have 9 different numbers that we'd have to add here. And if you think about it, that takes a lot of space and a lot of time to do. Using the standard algorithm, well, we're only going to have 3 different numbers here, which isn't as bad. So let's go ahead and do that. I'm going to keep track of the carries as well, because I do want to talk about what each of those numbers that we carry actually means. So 7 times 5 is 35. We're going to carry our 3. And where does that 3 come from? Well, I'm going to do that calculation over here. 7 times 5 is 35. So that 3 is the same as that 3. Maybe we'll put a box around both. So you can see why we put it over the tens digit when we're multiplying our ones, because this 3 actually stands for 3 tenths. So the place value of that 3 is the tens place. Similarly, all right, if we do 7 times 7, which is really 7 times 70, so it's 7 times 7 is 49, plus 3 is 52, but really what we're doing, because remember, this 7 stands for 70, so really we're doing 7 times 70, and then we're adding 30, since this is 7 times 7 tens plus 3 more tens. So this is 490. 7 times 7 is 49. Then you add your 0. Plus 30 is 520. So we put down our 2, our 20, if you will, and we carry our 5. So this 5 is, of course, in the hundreds place. So this 5 here stands for 5 hundredths. And finally, we keep going. 7 times 3 is 21, plus 5 is 26, but it's really 7 times 300 is 2100, plus 500 is 2600. So it's 2600, like that. So let's write that out. 7 times 300 plus 500 is 2,600. And we don't write a carry down, but we are carrying that 2 to the thousands place. So of course it has a place value of thousands. We continue. 9 times 5 is 45. So I left this place blank because really we're doing 90 times 5, not 9 times 5. This is 90 times 5. So we have to make sure we're over one place value. Okay, so it's 45. So I put down my 5 and I carry my 4. What's the place value of this 4? Well, some people would say, well, it's above, I put it above the tens, so it must stand for 4 tens. But it doesn't. You have to be careful here. So this is 90 times 5 is 450. So really, this 4 here stands for 4 hundredths. So you can kind of think, I like to kind of keep my carries in line. So I'll do my ones carries in one line, my tens carries in the next, my hundreds carries in the next, etc. And the reason I do that is it keeps the place values lined up for me. So this comes from my ones carries. This is my tens carries. So I have to think, since they're my tens carries, I have to add an additional 0 or move over an additional place value. And this then becomes, rather than tens, it comes hundreds, because it's over the tens, but you add an additional 10, you multiply by 10 again, you get hundreds. That's what happened here. So we had 90 times 5 is 450. So it's 450. This is hundreds. All right, let's do the next one. So 9 times 7 is 63, plus 4 is 67. So we put down our 7, and we carry our 6. But really, what that is 90 times 70. And we have to add our 400. So really, this is 6,300, plus 400 is 6,700. So that carried 6 that we just did, this guy here. What's the place value of that? That is thousands. So the 6 stands for 6 thousandths. You can think we're over the hundreds place, but it's the tens carries. So it's 100 times 10 is 1,000. So the place value of this is 6 thousandths. And finally, 9 times 3 is 27. And 27 plus 6 is 30. No, round color. 33. And again, this is going to be 90 times 300 plus 6,000. And you can check. I won't do it out. It's 33,000. So this guy here is 10 thousandths, of course. So hopefully you can see that. And then finally, 5 times 4 is 20. So I'll put a 0 here. I'm leaving two places blank. Some people put zeros in here. Some people like to do that. You don't have to. But if there is a 0 or not here, I am reading this number as 33,750. So what this number really is with the 0 in the ones place, etc. So let's continue on here. So we have 4 times 5 is 20. Put down your 0. Carry your 2. And again, let me do it in black since I was using black all along. And this comes from 400 times 5 is 2,000. So this guy here is 2 thousandths. And that makes sense. You can think of it. Well, it's over the tens, but we're in the hundreds carry because we're multiplying by the hundreds here. And 100 times 10 is 1,000. So this stands for 2 thousandths. Okay, we keep going. 4 times 7 is 28, plus 2 is 30. Put down your 0, carry your 3. So this 3 stands for, and you can check, 3 10,000ths. So we're in our hundreds place. Hundreds carry. 100 times 100 is 10,000. So that stands for 30,000. 3 10,000ths. And then finally, 400 times 300 is 4 times 3 is 12, plus 3 is 15. So really, oh, we're on color again, 15. So really what we're doing is it's not 4 times 3, it's 400 times 300 plus 30,000. So 400 times 300 plus 30,000. So that's going to be 120,000 plus 30,000 is 150,000. And of course, finally, we could say that this one here is our in the hundreds thousands place, of course. 100,000s. 100,000s. And of course, when we do the standard algorithm, we don't actually write all of that down over to the side here. This is just all pedagogical. This is so we understand what each of our multiplications is actually doing. So let's make sure we know what each number stands for down in the subproducts. Of course, this number here is 7 times 375. This number was 90 times 375, not 9 times 375, because we move over a place value. This is 33,750. That's 90 times 375. And the final number here is 150,000, which we got from 400 times 375. So this is 400 times 375. And if we add them all up, of course we're going to get 497 times 375, and which is 5, 7, 6 plus 7 is 13, carry your 1, 2 plus 1 plus 3 is 6, 3 plus 5 is 8, and we just have our 1 here, so 186,375. But the key here, I just want to make sure that these carries that we're doing, they actually have a place value attached to them. And that's important when you're teaching the standard algorithm to students. A lot of students will kind of make mistakes with what's going on here, or they won't understand. As teachers, I think it's very important to understand what each step of the algorithm is doing arithmetically or mathematically, just to make sure you know that, hey, this 6 doesn't stand for 600s. This is, in fact, 6,000s. It does have a place value imbued with it. So this is a very important example, and you will definitely see something like this on a future midterm or assignment or exam. So I would make sure you understand how these place values come about. This video should help you with that. All right, there are some other algorithms floating around, but I will say they're basically all partial products in disguise. And here's one that some of you may have seen. Back in probably the early 2000s, there was a big fad in math education where they like to draw boxes with diagonal lines in it. And so this is how this one works. If you want to multiply 24 times 37, you draw a box. You draw, since there's 2 digits by 2 digits, you kind of break that up just like you did for partial products. We're going to put some diagonal lines there. And now we're going to multiply as follows. So 4 times 7 is 28. So I'm doing this block here. So I'm going to put a 2 here and an 8 here, 28. Then let's do the next block. 4 times 3 is 12. 2 times 3 is 6. I'll put a 0 here and a 6. And 2 times 7 is 14. This should look very familiar to you if you looked at the partial products video or partial products section of this video that we just talked about. And then they say, well, just add on the diagonal lines. So let's do it. Here's our first one. There's just an 8, so we put an 8 here. Then we do 2 plus 2 plus 4 is 8. Then we do 1 plus 6 plus 1 is 8. And then we just have a 0 here, so we put a 0 or nothing if you like. And our final answer is, of course, 888, like it was before. So we write down 888. So if you look at what we did, I'll just write it out in partial products here. 24 times 37. So we had 28. Then we had, what do we do next? It was 7 times 20 was 140. Then we had 120. Then we had 600. So really, all that's going on is we're writing kind of this 28 is this 28. This 1, 2, this 12 is this 120. This 1, 4, this 14 is this 140. And this 0, 6 is this 600. But what it's kind of really doing is it's obscuring the place values a little bit. So in fact, all of these on the diagonal are in the tens place. So we have the ones place, the tens place, the hundreds place, the thousands place, etc. So that's all that's going on. But we're just not putting things in vertical lines according to place value. So it looks a little more complicated or something. But they like diagonal lines back in the day, so you just add on your diagonal lines rather than adding like this as you would. But it does kind of obscure here that this is actually, it's not 4 times 3. This is actually 4 times 30. So this is a little bit obscured what this stands for. With actual partial products, well, you know that you're doing 4 times 30 is 120. So while it's not wrong, it is a little more work to kind of draw a box with diagonal lines and then kind of add on the diagonals and then kind of interpret your answer as 888 like this. So I would say, especially if you had something, imagine if you had a 4-digit by 4-digit number here and you multiplied, well, you'd have to draw this huge box here. Imagine if you were doing that. So your box would look like this. And think about how that addition would go. It would be pretty infeasible. In fact, using partial products for something like this, you'd have 4 times 4 is 16 different numbers. So that would be pretty hard to do as well. Trying to keep track of 16 different sums along your place value here will be very, or I should say 16 different digits, and you're summing them. It would be very, very difficult to keep track of and take lots of space, and you'd be writing down lots of extraneous zeros. So the standard algorithms are not too bad for things like speed and efficiency and just taking up less space.